welcome to the Chemistry channel. So today in this video we're going to be talking about the constant pressure calorimeter. So before we get into what the constant pressure calorimeter is, let's first define what calorimetry is. So calorimetry. Calorimetry is just the study of heat flow. And we use an object or an instrument called the calorimeter to do so. And in this video, we're going to be talking about the constant pressure calorimeter. So right here, I've drawn you a simple diagram of what the constant pressure calorimeter is. And the constant pressure calorimeter is also given another name, and its other name is called the coffee cup calorimeter. So let's talk about the different parts of the calorimeter. So the first part that I want to identify is something called the reaction mix, which is this, which is a mixture of water, reactants, and products. So the reaction mix it contains three different things. So the reaction mix. So the reaction mix contains three parts. And the first part is the reactants. The second part is the products of your reaction. And the third part is the solvent, or in this case, water, because that's the usual solvent that you use in general chemistry. So the reaction mix contains your reactants of your reaction, the products of your reaction, and the solvent, which is in this case water. Now, the reactants and products are what comprise the system. So these make up your system, while the water makes up your surroundings. So it's part of the surroundings. So it's part of the surroundings, the water. Now remember that calorimeters, so recall, the calorimeters measure the heat of a reaction. So how do we measure the heat of reaction in a calorimeter? Well, we do so by the temperature change in water. So we measure the heat of reaction by the change in the water's temperature. So why the water's temperature? Well, the reactants and products make up the system, while the water is part of the surroundings. But what about all the other parts of the surroundings? Because remember, the surroundings is every part of the universe that isn't part of the system. So why do we only measure the temperature change of the water? Well, the answer is because of the coffee cups. So this little outline here is the coffee cup. And we assume the coffee cup to be a perfect insulator. So in other words, any change in temperature in the water is due to the reaction itself and not due to heat flow from the environment, because the coffee cup prevents heat flow from the environment and from the calorimeter itself. So perfect insulators prevent outside heat flow. Prevent heat flow outside of the reaction. So it prevents heat flow from anything other than the reaction itself, because the reaction is occurring inside the calorimeter. So in other words, any change in temperature of the water is due to the reaction only, and not from anything else. And remember that the water is considered the surroundings and the reaction itself is considered the system. So in other words, since we assume that any change in temperature of the water is due to the reaction itself and not from anything else, we can write this general equation. So, what is this equation telling us? Negative Q of the reaction is equal to Q of the water. So let's draw a little table here. And in here we'll have Q of the reaction, Q of water, and whether it is endo or exothermic. And this is for the reaction. So, when a reaction gives off heat, Q of the reaction will be negative. So remember that when any reaction gives off heat, which is the system, Q will be negative because you're losing energy from the system. And this process is referred to as exothermic. It's an exothermic process. So, since the reaction is giving off heat, what do you think will happen to the temperature of the water? Well, the temperature of the water will increase because heat is flowing from the reaction into the water. So therefore, the heat flow into the water will be a positive number. So Q of water will be positive. And this makes sense because if you multiply a negative times a negative, you get a positive. So this is what this equation is telling us. So what about if Q of the reaction is positive? Well, if Q of reaction is positive, this is indicating an endothermic process, so it's taking in heat. Now, since the coffee cup itself makes a perfect insulator, the only thing that the reaction could be taking heat from is from the water itself. So therefore, heat is flowing from the water into the reaction, giving Q of water a negative value. And if you use the equation above to check this, you'll see that a negative times a positive is equal to a negative. So that's what this equation is telling us. And this works off the fact that the coffee cup is a perfect insulator. So assuming that the coffee cup is a perfect insulator. So now that we have a general idea of heat flow inside the calorimeter, let's just identify the two remaining parts of the calorimeter. This right here, you may have guessed it, is a thermometer, which is used to measure the changes in temperature. And then you'll often have some type of covering on top of it. So now let's apply what we learned to how we can actually use the calorimeter. So let's bring our little equation back. So negative Q of the reaction is equal to Q of the water. So we know here that this reaction works when you assume that the coffee cups are perfect insulators. So how can we get delta H of the reaction from this equation? Well, you may recall that the coffee cup calorimeter is under constant pressure. So why is the coffee cup calorimeter under constant pressure? Well, let's go back to our little diagram here. And the reason why a coffee cup calorimeter is called a constant pressure calorimeter is due to the fact that it is exposed to the atmosphere. The atmosphere exerts a constant pressure upon the calorimeter and its contents. Therefore, the reaction and the calorimeter is under a constant pressure exerted by the atmosphere. So this constant pressure will be equal to around 1 atmosphere. So that's why it's called a constant pressure calorimeter. So back to this equation here. So what does this imply? Well, you may recall that under constant pressure, the heat lost or gained by the system is equal to delta H of the reaction. So what we can do here is replace delta Q of the reaction with delta H of the reaction. So this would give us a new form of the equation. Negative delta H of the reaction is equal to Q of the water. So we're very close to figuring out how we can calculate delta H of the reaction. So the only thing that we have to do now is figure out what this Q of water means. And in order to do that, let's do a little bit of algebra and math to get there. So in order to define what Q of water means, we have to define a new definition. And this new definition is called the heat capacity. The heat capacity of something is the heat that is required to raise a substance's temperature by 1 degree Celsius or 1 Kelvin. So why do I put or here? Well, the reason why is because degrees Celsius and degrees Kelvin increase at the same rate. So an increase by 1 degree Celsius is equal to an increase by 1 degree Kelvin. So mathematically, what heat capacity looks like in its integrated form is this. So C is the symbol for heat capacity. Q is heat, and then the change in temperature is the change in temperature of the object or substance. And the units for heat capacity are joules per Celsius or Kelvin. You can use either one, but you'll often find it in joules per Kelvin. So this is the heat capacity, right? So now that we know what the heat capacity is, let's apply what we learn, what we know about our calorimeter to this equation. So here is our equation once again for heat capacity, and we know that the coffee cup calorimeter is under constant pressure. And since we are under constant pressure, so this means pressure, delta H is equal to Q. So therefore, C is equal to delta H over delta T. So when you're under constant pressure, you can use either this form of the equation or this form, under constant pressure, which is the usual case for general chemistry. So before we get into more on this equation, I want to define one more term, and this term is the molar heat capacity. So this C represents heat capacity. So molar heat capacity. The molar heat capacity is the heat required to raise 1 mole of substance by 1 degree Celsius or Kelvin. So the symbol for molar heat capacity is C bar. So you usually put a bar under it. And C bar is equal to C over N, where C is the heat capacity, N is moles, and C bar is the molar heat capacity. And the units for molar heat capacity are joules per Kelvin times moles, or joules per degrees Celsius times mole. So we can use what we know here and plug it into our equation above. So recall that the heat capacity is equal to delta H over delta T under constant pressure. We know that C is equal to N times C bar, right? So N times C bar, and that's just using this equation above. So therefore we can substitute this into this equation. So therefore N times C bar is equal to delta H over delta T. And what I'm going to do here is put a little subscript P by this C bar here. And this is just indicating that we are under constant pressure, so CP bar. So now what we're going to do is we are going to solve for delta H. So solve for delta H. And delta H in this case will be equal to N CP bar times delta T, which is equal to delta H. And this will give us our first equation. So remember, since we're under isobaric conditions, Q, which is equal to delta H, will be equal to N CP bar times the change in temperature, where N is the number of moles, CP bar is the molar heat capacity, and then change in T is the change in temperature. So T2 minus T1. Now there is another form of this equation that is actually more commonly used, where instead of using the molar heat capacity, we use the specific heat. Now specific heat is the amount of heat required to raise 1 gram of substance by 1 degree Celsius or Kelvin. So the specific heat, instead of using moles, you use grams. So the equation will look identical, except instead of N and molar heat capacity, we use M to signify mass. And this CP bar here will be the specific heat capacity, or specific heat. And the specific heat is given the units of joules per gram times Kelvin, or joules per gram times degrees Celsius. And this is the more common form of the equation above. So now, since we showed how to get these equations, let's apply it to the equation that we started with. So remember, we said that negative Q of the reaction is equal to Q of water. And we know that since we are under constant pressure, that negative Q of the reaction will equal negative delta H of the reaction, which will equal Q of water. So now that we have this, all we have to do in order to find delta H of the reaction is substitute in the equation we just derived for Q of water. So delta H, negative delta H of the reaction, is equal to the mass of water that you have. So this is the mass of water, times the specific heat of water, so specific heat, times the change in temperature of the water. So this equation here will give you delta H of the reaction. So in order to get delta H of the reaction, we can just divide by -1. So therefore, delta H of the reaction is equal to Q of the reaction, which is equal to M times Cp times change in T. And remember, this applies to this stuff here, so I'll just make the arrows here as well. And this is the equation that you can use to figure out what delta H of the reaction is. So actually, I forgot to multiply by -1, so let's just fix that. So this is the equation that you can use in order to find what delta H of the reaction. As you can see here, we can use this equation to determine whether a reaction is exothermic or endothermic. So remember, for exothermic, so for an exothermic reaction, delta H of the reaction is negative. And this should make sense because for in the water here, so for delta T, if you have T2 minus T1 is equal to delta T, for an exothermic reaction, the water would increase in temperature. So therefore, T2 would be greater than T1, therefore giving us a positive value for delta T. And if you multiply a positive times a negative value, you get a negative, telling us an exothermic reaction. Now for an endothermic, it's the opposite. Your delta H of the reaction would be positive, and this would mean that heat is sucked out from the water, so therefore T2 would be less than T1. Therefore, T2 minus T1 would give us a negative number, and a negative times a negative would give us a positive. So this is just proving the table that we have above. So that is it for the constant pressure calorimeter. And in the next video, we'll be tackling the bomb calorimeter or constant volume calorimeter. So I hope this video helped you, and I hope to see you in the next one. See you around.